Today I'm going to give you an introduction to a kind of modeling that's called state space modeling. We're not going to go very much into depth in this class because we only have a couple of lectures left. But I want to give you enough information about this that you will be able to use it in cases where it proves to be more useful than the other kinds of modeling methods we've looked at, and that you have enough information to look it up and learn some more about it on your own. So to start out with, I'm going to lay out why we would use state space modeling and in what cases it'll be useful for us. If we think back to what we've learned in this class so far, you know that we start out when modeling a system by coming up with the differential equations that represent that system. Early on in class, we learned how to take a differential equation of a system that is a first order or a second order differential equation and match it to the standard form of a first or second order differential equation in order to find properties of the system like the damping ratio and the natural frequency. We saw that as our systems became more complex, just modeling the system from the differential equations would get to be pretty difficult. So we then learned something called the Laplace transform, which allowed us to put our differential equations into algebraic equations. This allowed us to more easily model systems that were more complex. However, we've also seen that as systems become more complex yet, even taking the Laplace transform and modeling the system that way can also become complicated and messy. So we have another way to simplify the modeling process, and that is through state space modeling. State space modeling is used to convert differential equations into linear algebra equations, kind of in the same way that the Laplace transform was used to convert the differential equations into algebraic equations. In state space modeling, what we end up with as a model of the system is a couple of matrices which define the system behavior. By expressing the system in matrix form, we can reduce the amount of substituting in that we have to do to reduce several equations into one single transfer function. So let's take a look now at how state space modeling works. State space modeling is based upon the concept of a system state. The system state is defined as the set of all information that is needed to define the system output at any given time. Let me give you a couple of examples of states for systems that we've looked at previously in this class. Here I'm showing an RC circuit. What information about this circuit would we need to know at any given time to define the output voltage? We might need to know the current in the circuit. And we might need to know the derivative of the current. Or perhaps we need to know the integral of the current. These things are neither the input nor the output, but they are what we refer to as states of the system. Things that, if we knew them, we would define the output relative to the input. When we're doing a modeling operation using the Laplace transform, trying to find a transfer function, we always have to get rid of these signals that are not the input or the output. In state space modeling, we don't necessarily have to get rid of these signals that are in between the input and the output. These signals can be our states. By allowing us to have states in the equations that we come up with, that can simplify our task of coming up with a system model. What we are after in state space modeling isn't a transfer function. A state space model looks like this. We're going to use the variable x to represent our states. Since we may have more than one state, the x is going to be a vector. And I'll indicate vectors by putting a little half arrow on top of the variable. Our state space representation will also be a function of the derivatives of the states, and we'll represent that like this. We'll also represent our output signal as y, and we'll represent our input signal as u. Now, whereas the mathematical trick with the Laplace transform is to take the Laplace transform and then get the equation to match the transfer function form, with state space, we're also trying to get our differential equations to match a particular form. And the form that we're trying to get it to match looks like this. We have two equations, and the first equation is our vector x dot. And then we have a matrix A, which is multiplied by our state vector, plus another matrix B, which is multiplied by our input signal. Then we have a second equation, which is our output signal Y is equal to a matrix C times the input vector, or times the state vector rather, plus D times our input signal. In order to get our differential equations to match this form, we have to identify what our state vector is. This is a little bit tricky to do because there isn't just one possible state vector that we could use for a given differential equation or a system of differential equations. We could use multiple different kinds of state vectors and still come up with the right answer. What makes our definition of a state vector correct is that if our state vector allows us to put the equations into this form, then we've chosen a good state vector. So I'm now going to show you a couple of examples about how we pick our state vector and then how we use that to put the equations into state space form. The first example I'm going to do is just the standard form of a second order differential equation. Here I've shown the standard form of a second order differential equation. In the past, when we've looked at the standard form, I've used x of t here and I've used u of t over here. I've switched that up now to use theta and v because I don't want to get confused between the variable that I have in my equation and the variable that we're using to represent the state vector and the input vector in my state space representation. So in this standard form, I'm going to assume that the input signal is v of t and that the output signal is theta of t. Just like we've done previously in class, identifying the input and output signals is the very first thing you want to do. Now the next thing I need to do is identify my state vector. To figure out what I need in my state vector, I'm going to take each of the signals that I have in my equation. In this case, the only signals that I have are theta and v. And I'm going to look at what is the highest derivative of each of those signals. Here, the highest derivative of theta is the second derivative. Since the highest derivative is the second derivative, that tells me that I need to have two state variables to represent the theta signal. One of my state variables is going to be theta, and the other state variable is going to be theta dot. If I had a theta triple dot in this equation, I would then need to have a third state vector to represent theta double dot. You always want to take the highest derivative and have one state variable for each lower derivative of that variable. Now, for the signal v of t, I don't need to have any state variables for that because the highest derivative of v of t is the 0th derivative. So I do not need to have any state variables for v of t. Now, I'm going to write my first state equation. The first state equation, if I scroll back up here, remember, is the derivative of the state vector is equal to some matrix A times the state vector plus some matrix B times the input U. Let's write that for our state vector. The derivative of my state vector will be theta dot, that's the derivative of x1, and then theta double dot, that's the derivative of x2, equals some kind of a matrix that I'm going to need to figure out, times the state vector, which is here x1 theta and x2 theta dot, plus some other matrix times my input. My input here is v of t. What I need to do now is fill in what goes in each of these places to make these two equations. Now, my first equation is the easiest because I have to write an equation theta dot equals something times theta plus something times theta dot plus something times v. Theta dot is equal to theta dot, so all I have to do here is put a 0 there and a 1 here and a 0 here, and this says that theta dot is equal to 0 times theta plus 1 times theta dot plus 0 times v. The second equation is more difficult because I have to get that from my differential equation up here. I'm going to solve this equation for theta double dot, and I'm going to write that down here. I wrote this equation in an order that will make it easy for me to fill in these other elements of the matrix. Theta double dot is equal to negative omega n squared times theta. So negative omega n squared has to go here because that's being multiplied by theta. Then negative 2 zeta omega n goes here because that's the coefficient that's being multiplied by theta dot. Finally, g omega n squared goes here because that's the coefficient being multiplied by v of t, my input. Now, I'm not quite done with my state space representation yet because remember there's a second equation that we also need to write. That is this equation here. Y is our output signal, which in our case is theta of t. So I'm going to write this equation using our variables down here. The output theta of t is equal to something multiplied by my state vector, which is theta theta dot plus something times my input, which is v of t. Well, this equation also is pretty easy to fill in because theta of t is one of our state variables. So theta of t is equal to theta of t. I can just put a 1 here and a 0 and a 0, and that gives me a true equation. Now, in order to simulate this system and analyze it, all we really need to know are these matrices. This one's called A, this is a matrix called B, this is C, and this is D. The magic of a state space representation is that these 4 matrices are all you need in order to define the system. Now, in class, we're going to look at how you can build a state space representation simulation using things like MATLAB and Simulink. And next time, I'm going to show you another example that's more complex than this simple standard form of a second-order differential equation. Just like we saw with the Laplace transform method, certain system equations are more difficult or complicated to get into the format that you're looking for, either the transfer function format or in this case the state space representation format. So for today we'll just take a look at this simple example, and next time we'll look at a more complex example.